So therefore, each of these can provide at most one solution, so I get a bound of 2. Now for this orbit, I'll pick P0102. You can see there's only 3 ways we can complete this. It doesn't take much work. It's very quick to determine the parity maps. And each of these meet the hypothesis of that parity graph lemma. As you can see, each cycle has a center vertex in it. So that gives me at most 3 solutions for those. Now, for P0213, we get 2 parity graphs that meet the hypotheses, but 2 that don't. But each of these that don't, well, let's take a look at this. If I know this entry and this entry, then I get this odd, which gives me these odds. This odd gives me an entry in the center, so not only does it give me these odds, it gives me these 4 evens, and this even completes the rest. So I know that this map gives me puzzles, gives me at most 4 solutions. And similarly, this map gives me at most 4, and this gives me at most 1, and this gives me at most 1, because they meet the hypotheses of the parity graph lemma. So I get a bound of 10 there. I'm not going to do the rest. It's similar. These were the 4 graphs I just talked about. You can see these 2 don't meet the hypotheses, which is why we ended up with 4 instead of 1. So this was the equation. We get these, we find these bounds, and we know they must be equal because that's the only way we can get them to add up to 576. So now we have fully the number of solutions for each of the puzzles. You see we get puzzles with 1 solution, 2 solutions, 3 solutions, 4, we skip 5, 6, and 7, we jump to 8 solutions, there's 2 different orbits there, we go to 10, and then finally at most 12 possible solutions. From this we could even try to guess how Brian Hayes ended up choosing the original puzzle. Like, for instance, if he picked 6 clues at random, we could say what the odds were of getting a puzzle with a unique solution. What if he picked the square? Well, it's better if he started off by picking a diagonal square to generate a puzzle. We can sort of guess how he ended up with that to begin with. But I'd like to say what happens now if I change the group a little bit. So what happens when we change the pattern to a different group? Well, we only have one choice. We're going to keep order 4, and there's lots of different ways to think about the Klein 4 group. When I need to, I'm going to use this to the group of units in modulo 8, 1, 3, 5, and 7, when I need to pick a way to think about it. But let's think about what's similar when we move over to the Klein 4 group. Well, we still need odd cages. As a matter of fact, we need it even more here, because we end up with 4 solutions, because we can add any element to each of the cages. Each of the elements squared is the identity, so if all the cages are even, I can basically multiply a solution by any element in the group and get another solution to the same puzzle. So we still need odd cages, and we still end up needing that cage pattern that we had in the Z4 case as well. So the little lemma that we proved that counts the number of solutions still holds. It holds over any group. We end up with the order of the group minus the number of roots. Now, it turns out if my clue is the identity, I'm going to have 4 roots, so I'm going to have 4 minus 0 possibility, 4 minus 4 solutions, which is 0. And in the other case, I end up with 4 solutions each. So no solutions if my clue is the identity, and 4 solutions otherwise. But we immediately get this lemma, which is really strong and definitely not true in Z4, which is adjacent equal clues imply no solutions. For example, if these 2 are adjacent, we see that if I were to force a line here, this would have to be the identity, and we just said we can't have a 2 cage with the identity as a clue. So no solutions if we have adjacent equal clues. Another thing is I'm going to just define home corners and away corners. A home corner is just going to be a corner entry equal to the clue in a corner of the puzzle. And an away corner is going to be one that's not equal to the clue. Now, it turns out that if a corner cell matches the clue for its cage, the other cage entries are equal to each other and not the clue, and that gives us 3 possibilities. And here's why. Well, if I put the clue in the corner, I know that these 2 have to give me the identity, so they have to be the same, and I'm done. And they also can't be equal to the clue. That's why there's 3 possibilities, not 4, and that's because of the Latin square condition. For an away corner, we actually get a stricter lemma here. The other entries have to be distinct and not equal to either the corner or the clue. So all 4 elements of the group have to show up. And this is because, let's look at this situation where x is not equal to c. Well, I know that neither of these can be x. And if one of these were C, then the other two would be forced to be the same because they would have to be the identity, and that would violate the Latin square condition. So these can't be X, they can't be C, but they also can't be equal because that would force X to be equal to C. And the switch trick is even stronger over the client 4 group because I can switch any two elements with the other two. And that's because, well, the product of everything is the identity, and each of these elements with their own inverse, so I can just multiply this by CD to get that. So I can switch any two entries with two different entries. So I'm getting a lot of the same things that I did last time, and we can actually sum up what happens in this situation rather quickly because of that. So left multiplication only ends up being an automorphism in whatever group we're in if the group element we're left multiplying with ends up being the identity. But here, we can use the fact that all of our cages are 3 cages. So we don't need it to be an isomorphism. If I know that G squared is the identity, like it is for any G in the client 4 group, if I take the clue and I map it over, and I take the elements and I map it over to a new puzzle, well, gxyz is g cubed xyz, so this works out nicely, and these left multiplication maps end up being invertible, so not only does it send solutions to solutions, I'm also not creating any new solutions as well. So what does the left multiplication map do? Well, if I left multiply, and let's move over to 1, 3, 5, 7 for this. If I left multiply by 3, I switch 1 and 3 and 5 and 7. If I left multiply by 5, I switch 1 and 5 and 3 and 7, and then 7 switches 1 and 7 and 3 and 5. So I get this group, which preserves the number of solutions when acting point-wise on my puzzles and on my squares.
You're still only talking about the 4x4 case?
4x4 client 4 group, right.
So that's very beautiful mathematics, right? You can do everything by brute force, because that's okay.
So I'm going to call this group N, and this ends up preserving the number of solutions. However, I still have the space of automorphisms, because we looked at the maps that weren't automorphisms first. And the space of automorphisms is isomorphic to S3, and it's equal to those permutations. And we already showed that automorphisms are solution-preserving maps, so everything here maps solutions to solutions. And then it turns out that S4 is the semi-direct product of N and H, or just, you could just think about it as N and H end up generating all of S4, so we can extend this to the S4 action. So we have a much bigger group action, and we have the dihedral group still. We can still rotate, we can still reflect, so we end up with a very large group acting on our puzzles. And that breaks everything down to these orbits. So once again, I'm organizing this by a number of distinct clues here, and then the stabilizer, and the order of the stabilizer, and the size of the orbit, and the number of solutions. And I've decided that I would fill in these entries for us, because we have adjacent equal clues in those situations. And I know that that implies no solution. So basically, we only have 3 things we need to find here in order to completely sum up what happens in this case. We get this equation from multiplying these 2 columns. And let's look at one of those 3. If I look at the 1, 3, 1, 3 case, I know that this is 1 and this is 3. So this 2 cage, if I seal it off, would have to have a clue of 3. Okay, well, in order to get a 3, I either need a 1 or a 3 or a 5 or a 7. So I get this kind of map without knowing whether the A's are representing the 1 and the 3, or the A's are representing the 5 and the 7. But remember, I could use my home and away corner lemmas here. So if this was an away corner over here, this A would have to come from 5 or a 7. So that would mean these would have to be the other 2 entries. It would have to be 1 from this and 1 from this, which would contradict the fact that these are both coming from B. So I know that this must be a home corner, either a 1 or a 3 from that lemma there. So basically, once I know that the A's have to be from 1, 3, and the B's have to be from 5, 7, this is the same thing that we had in Z4 with the odds and the evens. So we get something similar to a parity map. Now these green entries determine the square, which implies that there's at most 8 solutions. And then we have our switch trick again, so we could switch the left and the right column, the top and the bottom rows, and the 4 center entries. So this shows us that there's also at least 8 solutions. So we get 8 solutions in the 1-3-1-3 case. Now we have 2 other cases. I'm going to leave them out in the interest of time, but I'll just say something. It's not. We can show that puzzles in the 1-3-1-5 orbit are determined by the value of any corner with 1 as a clue. So that gives them 4 solutions at most. And puzzles in the 1-3-5-7 orbit are determined by the values of any 2 opposite corners. And those opposite corners can't be the same, otherwise it can't be completed into a solution. So that limits them to at most 12 solutions, and that completely determines the table right away. So this sums up exactly what happens over the Klein-4 group. I'm going to leave you guys with this exercise. This was an almost lemma, which I found interesting. If you have a solvable puzzle with solutions, the set of entries, or that's redundant, but the set of entries equals the set of clues, except for puzzles in the 1-3-1-5 orbit. And those puzzles have exactly 1 solution that violates the fact that the center entries have to equal the corners. But for every other puzzle it works, and there's only 1 exception. Okay, I'm going to take the last few moments really quickly to talk about Z5, what happens when you blow things up a little bigger. I'm still going to require no 1 cages. I'm going to require the horizontal and vertical reflective symmetry, but I'm also going to enforce a maximum cage size of 5 to keep things from getting too ridiculous. The number of cage patterns still blows up here. There's a lot of different patterns. So how am I going to organize the cage patterns? In the last situation, we only ended up with 5. Here we end up with much more. So what I'm going to do is I'm going to organize these by the number of clues it takes before all the values of all the other clues is completely determined. And then I'm going to list 1 representative from each class. So here are the 0 clue patterns. You don't need any clues to determine what each of these clues have to be, because 0 plus 1 plus 2 plus 3 plus 4 is going to add to 0. And of course, this doesn't have very much hope of having unique solutions, because every Latin square is a solution to this puzzle. Okay, now if I know what this clue is and this clue is, just to show you how I'm organizing this, I immediately know what clue I would need here, because I know what each of these rows adds to. And I know that this must be 0 and this must be 0. This cage pattern has no chance of unique solutions, because I could always switch the bottom and the top here. For the 4 clue patterns, it's sort of obvious that 3 of these have no solutions. I can switch these 2 columns if I have a solution, and that will map solutions to the solutions. In the bottom here, I could switch the top and the bottom rows, and that shows that we don't have unique solutions. Over here, it's not quite as obvious, but every puzzle ends up, it's not hard to show that every puzzle has to have at least 72 solutions in this case. And this might look like it violates my no cages bigger than size 5, but this is representing a whole class of puzzles. So this is really representing the puzzles with lines here and the puzzles with lines there as well. So when you get to 6 clues, you still get no puzzles with unique solutions. This one I can switch the top and the bottom. I can switch the 2nd and 3rd rows here to get a new solution if I have 1 solution. But once I get to the final, the 8 clue patterns, I'm starting to get some unique solutions. Now down here in the bottom, I can switch the first 2 columns to turn a solution into a new solution. So this one doesn't have any hope. But the other 3 all produce unique solutions. So let's just, I know I don't have a lot of time, but let's just talk a little bit about these puzzles. So this cage pattern ends up giving me solutions, puzzles with 1 through 6 solutions, skips 7, skips 9, 10, 11, and has puzzles with 12 solutions. And we have over 13,000 puzzles with unique solutions. No, it's not in the OAIS. I mean, these kind of end, but I can fill it in with zeros after that. That's a good point. I hadn't thought about that. Zeros afterwards. Each of these could be in the OAIS.
It's too finite.
This cage pattern ends up with 35,000 puzzles with unique solutions, and puzzles with solution numbers skipping 10 and then jumping to 11 here. And then for the 10th cage pattern here, for the final one, this is the richest of the cage patterns in the Z5 case. We end up with solutions from 1 through 13 possible solutions. And we end up with 2,000 puzzles that have unique solutions here. So just really quickly, what happens when we do the same tricks that we did before? Well, the automorphism group ends up being Z4. And then we can allow things to act pointwise on the squares and puzzles. If we add to the 2 cages without adding to the 5 cages, this is going to preserve the number of solutions. Obviously, if I add 1 to each of these 5, I need to leave these unchanged. So that also preserves the number of solutions. What we can do is we can take solutions and we can switch the 2nd and the 4th rows to, and there's a dependency amongst the clues here that gives us a similar action on the puzzles that preserves the number of solutions. And then finally, we can still rotate and flip. We can't rotate 90 degrees, but we can rotate 180 degrees. So we put all of that together and we get a group of order 160. Unfortunately, there's enough puzzles that still makes this very, very large, but the puzzles with unique solutions fall into 13 of these orbits only. So I actually have a handout here. There. I have a handout here, so you guys can try one puzzle from each of the orbits. You can see that when you're actually solving them, the information that ends up being immediately given does feel different in each of these different orbits. So this is something you guys can try later on. You can take that with you. Now, when you start to get to the Z6 and the D3 case, just sort of the number of cage patterns blows up a lot. I tried putting some restrictions that made it kind of tight, in my opinion, and I already got 170 cage patterns in the tightest one, so that seemed rather arbitrary to start settling down on these and doing that in the Z6. So with that, I'm going to end this here.
I'm going to submit them to New York Times.
It's a good idea.
Also, question. Can you do it for final fields? So you do only...
Right, you do it with 2 operations.
Yeah.
I like that idea. I haven't thought about that.
With final field, you have to division.
Yeah. I mean, KenKen puzzle standard division is possible, you know, when they do that in the New York Times puzzles and everything like that. So, yeah, no, I hadn't thought about tossing in a second operation and trying to classify.
You're not dreaming about these, are you? You're not dreaming about these, are you?
Oh, I definitely am dreaming about it.
We're really into it.
So, some of the OEIS people were contributing things that were infinite pseudo-coords. That way you get rid of the boundary. And I can tell you about that sort of.
Well, thanks for a beautiful talk. Hope to see you next semester.